All right, this is part 2 of my of our lecture on flexural design. We just talked about the section in the spec, F1, that talked about our phi factor and our CB factor, which was if we have a non-uniform moment distribution. So now we're going to talk about F2. F2 is for a doubly symmetric, compact, I-shaped members and channels bent about their major axis. Compact, what does that mean? It means nothing's going to buckle before we reach our plastic moment. If we go back to and look at our table user note F1.1. Right? Section F2. Doubly symmetric I-beam or channel bent about their major axis. Compact flange, compact web, yielding, and lateral torsional buckling are the 2 limit states that we need to take into account. If I go and look at F2, we have our 2 limit states, 1 yielding and 1 lateral torsional buckling. I'm not going to write out these equations because the second one's pretty long and I'm lazy. Right? So my nominal moment, my MN, for a doubly symmetric, compact, I-shaped beam or a channel bent about the x-axis, MN is the lower value of MN yielding and MN lateral torsional buckling. Equation F2-1 is how I calculate the nominal moment for yielding. This is my plastic moment. It means my entire cross section has yielded. And I use my plastic section modulus. That's Z, right? My yield stress and my plastic section modulus. So I'm going to check yielding and I'm going to check lateral torsional buckling. If we think back to this lovely thing right here, this lovely diagram, if my brace length is less than LP, and that this is what you're about to start seeing in equation form, if my brace length is less than LP, I'm going to have plastic yielding before I have lateral torsional buckling. So I don't have to count for it. I don't have to calculate it. If my LB is less than my LP, lateral torsional buckling is not going to occur, and my nominal moment design strength is my plastic moment, plastic yielding MP. If I'm between LP and LR, right, that's where I have my inelastic lateral torsional buckling. Again, let's go back to this, right? If I'm between LP and LR, here, I'll go back one further. Inelastic lateral torsion of buckling between LP and LR. Then I get to calculate my equation, which is basically, right, this is my MR, which accounts for residual stresses. This is a straight line interpolation, is all this is. Right? I'm basically interpolating from here to here. It's a straight line if I'm somewhere in this range. And I get my added bonus of my little CB factor if I want to take it into account. No matter what, this nominal moment cannot be greater than my plastic moment. There's always that cap. If I have an unbraced length greater than LR, I have elastic lateral torsional buckling. Where I calculate my nominal moment as a critical stress, which is calculated using this equation, this big long thing right here. It's kind of like your critical stress in compression. Right, that critical stress corresponded to Euler buckling. Right, we're buckling still, lateral torsional buckling. So that's what this is. It kind of looks similar to that, right? There's that pi squared E over LB over R squared, right? Right, pi squared E over your slenderness ratio squared. And there's some other stuff in there. Your JC, that's your moment of gyration, is that right? Oh, jeez. So many things. Torsional constant, torsional moment of inertia. Yep. Let me see. Probably says right there. Your J is your torsional constant. SX is your elastic suction modulus. HO is your distance between the flange centroids. And there's some other ways to calculate that RTS, which is related to your radius of gyration. All right. Now notice this is talking about SX. Why is this talking about SX? Because it's elastic. Your SX is your section modulus, right? I over Y. Your moment of inertia divided by the distance from the centroid to the extreme fibers. Whereas your ZX is your plastic modulus. Your SX is not, because you're assuming it's elastic, right? So these are checking for lateral torsional buckling of a doubly symmetric, compact, I-shaped member and channels bent about their major axis. This is F2. Here's some more of those equations in F2. We have our limiting brace length for plastic yielding. That's LP. Limiting unbraced length, basically. Right? If I'm less than that, if my unbraced length is less than that, I'm going to reach my yielding moment, my yielding plastic moment, MP, before any buckling occurs. If I have my LR, which is my limiting unbraced length for inelastic, right? Lateral torsional buckling. If I'm between LP and LR, I'm going to have elastic lateral torsional buckling. If I am greater than LR, I'm going to have elastic lateral torsional buckling. Okay? Now let's do one example. And then I'm going to do a second example live with you all next time we see each other. Right? So is the compact and laterally braced, and it means continuously laterally braced. Section sufficiently strong to hold the given loads. I need more slide. score. Okay. So, what's my first step? My first step would be calculate how much it needs to be, right? I can calculate, it's a load subject, or it's a beam subjected to a distributed load. I can calculate a factored, I'm going to go down here. A factored distributed load. WU 1.2 WD plus 1.6 WL, right? WU equals 1.2 times 1 kip per foot plus 1.6 times 3 kips per foot. As my live load, I get a uniformly, or a factor distributed load of 1.2 times 1, 1.6 times 3, 6 kip feet. And I just made an error because I just realized this is not including the beam weight. So my dead load is actually, my dead load 1 kip foot plus a 44 pounds per linear foot. Alright, and we're not going to do ASD. So this needs to change 1.044 kips per foot. Alright, my beam is 44 pounds per linear foot. I'm going to add that to my dead load of 1 kip per foot, 1.044 kips per feet. And get a factored distributed load of 6.05 kips per foot. So now I need to figure out from that, what is my maximum moment? And you did all that work back in structural analysis, and maybe you have this one memorized off the top of your head, but you could also go to the shear and moment and deflection tables, starting on page 3-208. It's in your beam part. All right. Way up here. Table 3-23, shears and moments, right? Uniformly distributed load, maximum moment, WL squared over 8. Again, that might be something you remember. Sometimes you forget. It's fine. Okay. My maximum moment. MU is WUL squared over 8. So that was 6.05 kips per foot times the length of my beam, 21 feet. Divided by 8. I need to make sure that my beam can hold a capacity of 334 or 333.5. 0.6 maybe if you didn't round it all. Kip feet. Okay? So, that's how much I need. My next question is, do I have the capacity? Well, this is a doubly symmetric, right? It's a W21 by 44. W21 by 44. We could probably go look at it. In the tables. It'll probably tell us. Oh, it says it's already compact. So we'll just assume it's compact because it told us that it was. And it's continuously laterally braced. So if I go back to chapter F in my spec, I can go to section F2 because I have a compact I-beam about its all right. So my first limit state that I need to check is yielding. Phi mn equals phi f y z x. Right? So I go and look up the Z value. I know my Fy. It tells me before 50 KSI. My Z value of a W21 by 44. W21 by 44. My ZX 95.4, right? 44, 95.4. This should be on page. It might look a little bit different. This is an outdated PDF. So it's on page 1-21. Right, my ZX is what, 95.4 inches cubed. FY is 50 KSI. So my phi MN is 0.9, 50 KSI, 95.4 inches cubed. And I get 140.4 kip inches. Divided by 12. Is that right? Hold on. Oh, okay. I was like, wait. 0.9 times 50 divided by 95.4. Oh, geez Louise. I should get 4293 kip inches, or divided by 12, 358 kip feet. Okay, so that's greater than my U. 350, let's not put any extra. All right. So far so good. Now my question is, I have two limit states for this type of member. LTB yielding and then lateral torsional buckling. Do I have to calculate the lateral torsional buckling nominal moment capacity? No, because this is a continuously laterally braced section. That means my unbraced length is 0. My unbraced length is 0 because it's continuously laterally braced. So, no matter what, my LP, my length between yielding and inelastic lateral torsional buckling, it's going to be greater than 0. So I don't have to check right, if your lateral bracing is less than LP. Right, that's directly from here. F2, doubly symmetric section. If my LB is less than my LP, the limit state of lateral torsional buckling does not apply. So, since my LB is 0, I don't have to check lateral torsional buckling. Therefore, my question is, my answer, I guess. Let's write an answer somewhere here. My FEMN is just the one from yielding, 358 cubic feet. And it is greater than my MU, which was 333 cubic feet. So, yes, sufficient. That was the answer. That was the question. Okay? I will leave the second example for next time we are together. And I hope you all have a great day. Thank you.